So this is part 2 for the year 2020, and this part 2 we are going to solve 10 questions, and all these 10 questions are from the mains. In the part 1 we solved also for the year 2020, and they were close to 15 questions. Okay. So in the first question, it states that in the circuit shown in the figure, the total charge is 750 microcoulomb and the voltage across capacitor C2 is 20 volt. Then the charge on capacitor C2 is. Basic figure is given to us. We have supplied voltage V and we have capacitor C1, and there is C2 and there is C3. C2 and C3 are parallel with each other and their combination is in series with C1. And we are given that the voltage across C2 is given to us as 20 volt, and we have to find out the charge across this capacitor. Okay, so let me redraw this figure. So this is a C1, C2 as well as C3, and the voltage is our plus minus, and let us assume that the voltage drop across C1 is our V1 and C2 and C3 are in parallel. So voltage drop across both will be same. So across C2, let us suppose we call this as V2. Similarly across C3, that voltage drop also will be equal to V2. And we are given that the total charge on this entire system is 750 microcoulomb. So we are given that total charge, let us suppose that is our QT, it is given as 750 microcoulomb. Okay, and okay, so we can say write the equation, and we say let us suppose through here the charge flowing is QT rather, and it is being divided into two parts. On from C2, let us suppose charge is flowing is our Q2, and from C3 let us suppose the charge is our Q3. Okay. And so from here also we are going to get as QT. So we can use the node equation for our charge conservation, and based on this we can write that our QT will be equal to Q2 plus Q3. Okay. And we are given, or we can see that our C2 as well as C3 are in parallel. Therefore, you can say our C3 and C2 are in parallel. Therefore, we can say that the voltage across C2 will be equal to voltage across C3, and voltage across C2 is given as 20. So across C3 will be also equal to 20. and which we have said is common voltage, that is our V2. So based on this we can find out our Q3. So we can say our charge Q3 will be equal to C3 multiplied by voltage across capacitor C3. C3 is given to us as 8 microfarad and VC3 is our 20. So this comes as 160 microcoulomb. So we got the charge across C3. Now using equation 1, we can find out the charge across C2, that is our Q2. So from equation 1, Qt we know is our 750 microcoulomb is equal to our Q2 plus Q3 we found out is our 160 microcoulomb. Therefore we can write that our Q2 will be equal to 750 minus 160 microcoulomb, and this comes as 590 microcoulomb. Okay. So we are supposed to find out the charge across C2, which is option 2 is correct. Next question. A 10 microfarad capacitor is fully charged to a potential difference of 50 volt. After removing the source voltage, it is connected to an uncharged capacitor in parallel. Now the potential difference across them becomes 20 volt. The capacitance of the second capacitor is. So here we are given that initially, let us suppose we have a capacitor C1 and it is connected to a potential difference of, let us suppose, V1, and the charge on this is our Q1. Okay. And when in the second case we are connecting our this C1 across another uncharged capacitor, whose capacitor we are going to find out, let us suppose that is our C2 and this is our C1, and it is given that the potential difference across them becomes 20 volt. So if V2 is the potential difference across both, and that V2 is equal to 20 volt, and we have to find out the C2. Okay. So in this case we have to keep in mind that the charge will be conserved. Okay. So therefore we start from there only. We say that our charge conservation, which means that the total initial charge will be equal to final total charge. And initial charge we assumed is our Q1, and the final total charge is, let us suppose, QF. So we can say Q2 rather. So we can say our Q1 will be equal to our Q2. So we can find out our Q1. Q1 is our initial charge, and we can find out this Q1 will be equal to C1 multiplied by V1, which gives us 10 microfarad multiplied by supply voltage of 50. So this gives us that our Q1 is equal to 500 microcoulomb. So therefore we can write that our Q2 will be equal to 500 microcoulomb. Okay. And we can also find out the formula for Q2. So for that we require that our equivalent capacitance and this is when C1 and C2 are in parallel. So we get our C equivalent will be equal to C1 plus C2, and based on this, and the common voltage across them is given as V2. So we are given that common voltage is our V2, value is given to us as 20. So based on this we can write the formula for Q2 will be equal to our C equivalent multiplied by V2. C equivalent is our C1 plus C2 and multiplied by V2. We substitute the values. Q2 is our 500 microcoulomb. So this becomes 500 10 to minus 6 is equal to C1 is known to us is our 10 into 10 to the power minus 6 plus C2, and V2 is also known to us is our 20. Therefore we can solve this, and let us suppose that the value of C2 is also in microfarad. Therefore we can take this as common, and this will be 10 to the power minus 6. So this 10 minus 6, 10 minus 6, and this 0 goes by 0, and 250 goes by 25. So we get this as 10 plus C2 is equal to 25. This gives us that value of C2 will be equal to 25 minus 10, giving us 15 microfarad. So option 3 is correct. Option 3 is correct. Next question. We are given, consider a sphere of radius r which carries a uniform charge density rho. If the sphere of radius 2 by r carved out of it, as shown, the ratio electric field of A at point A and electric field at point B of the magnitude of electric field EA and EB respectively at points A and B due to the remaining portion is. Basic figure is given to us. We have a bigger sphere of radius r and a small sphere of radius r by 2 is removed from it, and we have to find out the ratio of electric field at A as well as B. So in this case we can redraw this circuit, and for that we consider that the removed portion is having a charge density of plus sigma as well as minus sigma. Okay. And our complete sphere is already given, that is our plus sigma. So therefore we can redraw this circle, or we can say this figure, that we have a complete sphere without any portion removed, and plus that will be our removed portion, like this. So we can draw this, and actually here it should be minus, not plus, okay, because from the complete sphere, and A is the center of that. So this is our point A, its radius is R, and diagonal opposite we have a point B. Okay. And for this smaller radius, smaller, you can say sphere, its radius is R by 2. So this radius is given as R by 2. So point A is lying on its peripheral, and point B is outside of the sphere. Okay. So this is the basic, you can say, and the distance between A and B is our R. So complete distance of point B from the center of sphere will be R plus R by 2, which gives us 3R by 2. So like I said, we can say that the empty sphere, consider the empty space having charge density as it is rho, plus rho and minus rho. And in the first case, we are going to find out for complete sphere, that is, let us call this as figure 1, and this is our figure 2. So we can say that our for figure 1, we are given that our charge density is plus sigma plus rho. So therefore we can find out the total charge on the sphere will be equal to, let us suppose we call this as Q1. Q1 will be equal to charge density multiplied by 4 by 3 pi r cube, and electric field at point A and electric field at point, okay. So from figure A, we can say electric field at point A electric, okay, let me solve for the other one also. You can say for figure 2, total charge on the sphere let us suppose that is Q2 will be rho multiplied by 4 by 3 pi, and radius is our r by 2 whole cube. So net electric field at point A, and in the first case the point A is at the center of the sphere, and then second case it is on the periphery of the, you can say, figure 2. So we can say that electric field at point A. For figure 1, point A is at the center of the sphere, and for figure 2, point A is at the distance r by 2. Point A is at the distance r by 2. Therefore, we can write that our electric field EA, okay, we are only interested in magnitude for the, because point A is at the center, so we are going to get this as 0, plus electric field is at a distance of r by 2 for figure 2 will be equal to plus K, and we found out the charge is our rho, charge was Q2, let me write here Q2. So this comes as K Q2 divided by distance is r by 2 whole square. So we can substitute value of Q2, this comes as K multiplied by 1 by r2 whole square, and our Q2 is our rho 4 by 3 pi r by 2 whole cube. This r by 2 and cube goes away, so we are left with only that our EA will be equal to, we have this as K rho and 4 by 3 pi multiplied by r by 2. So this is the electric field at point A. Now we find out the electric field at B. Electric field at point B, and for point B, from the figure 1, the point B is at the distance r from the center, and from figure 2, that point B is at a distance of 3r by 2 from the center. Electric field at point B, you can say from figure 1, point B is at a distance of r. Therefore, and from figure 2, point B is at a distance of 3r by 2. Therefore, we can write the equation that the electric field at point B will be equal to our K, and we are having a charge of Q1 divided by distance is of r, and this r square minus K charge is our Q2, and at a distance of 3 r by 2 whole square. One second, Q2 we found out. Yeah, Q2 already we know. We substitute value of Q1 and Q2. We can take k as common, and we have q1 is equal to our, the denominator we have r square, and this is rho multiplied by 4 by 3 pi r cube, and minus, in the denominator we have this as distance of, and in the numerator rho minus 4 by 3 pi r, and its radius is r by 2 whole square. And this square goes by the cube, and we can take some things as common, then we can just solve it. So from the first part we can write this as k rho 4 by 3 pi, and inside we are left with r minus, this comes as r square by 4 multiplied by, this will be 4 divided by 9 r square. 4 by, one second, r cube, my mistake. R cube. So this comes as our r cube, and we have this will be our 8. Okay, so this square goes by this cube and 8 goes by 2, so we can take r also common, and this will be our k rho 4 by 3 pi r 1 minus 1 upon 18, and this comes as 17 upon 18, so this comes as k rho 4 by 3 pi r multiplied by 17 by 18. So we found out our electric field B, and we need the ratio. So we can say electric field A to the electric field B will be equal to, B is our k rho 4 by 3 pi r, and (17 by 18), and electric field due to A is our k rho 4 by 3 pi, and we have this as r by 2. So we can cancel k rho 4 by 3 pi r, and r, it goes away. So we are left with only 1 by 2 multiplied by 18 oblique 17, and now 18 goes by 9, so this comes as 9 upon 17. So the ratio, we have our electric field A upon electric field B will be equal to 9 upon 17. Okay, this is nothing but 18 upon 34. We can just multiply it by 2. This comes as 18 upon 34. So therefore option number B is correct. Option B is correct. Next question. We are given that an electric dipole of moment P given as -I minus 3j plus 2k into 10 to the power minus 29 coulomb meter is at the origin. The electric field due to this dipole at a distance of r, that is plus I plus 3j plus 5k, is parallel to, and we are given that the dot product of this radius vector and the dipole moment is 0. Okay. And we know the general formula for the dipole moment, electric field due to dipole moment. So we can say that our electric field due to a dipole electric field due to a dipole at a point R, at a point R due to a dipole P at the origin. And if that electric field is given as E, so this E will be equal to K multiplied by 1 upon R cube, and this is equal to our 3 dot product of the dipole, and we have this is our unit vector, and minus the dipole vector. Okay. And our R unit vector is equal to vector R divided by its magnitude. But we are given that the dot product of our R dot P is equal to 0. Therefore, we substitute here, we get our electric field E will be equal to, this will be K multiplied by 1 by 3, and we have this as minus, and then it is our dipole moment. So obviously from here we can say that the electric field is proportional to negative of the dipole moment, and we need only to the direction. We are not interested in other thing. Therefore we can say that our electric field is parallel to, and P is given to us as is parallel to, we can write this will be equal to minus of, and we have this as minus of I minus of 3j and plus of 2k. So this comes as I plus 3j minus of 2k. So we have this as plus I, only is option C is correct. Option C is correct. Next question. We are given a charged particle of mass m and charge q moving under the influence of a uniform electric field E I unit vector and a uniform magnetic field B K unit vector follows a trajectory from point P to Q as shown in the figure. The velocities at point P and Q respectively are V I unit vector and minus 2V J unit vector. Then which of the following statements A, B, C, D are correct? Trajectory is given to us. So basic figure is given to us. We have a point P. It is at a distance of A from the origin. Point Q at a distance of 2A from the origin. And electric field is along x-axis and magnetic field is along z-axis, which is perpendicular to the xy plane. and velocity at point P is along x-axis and at Q is along y, that is negative y-axis. And we are going to find out mostly it is that we have to find out the value of electric field, net electric field, the work done, and the difference between the angular momentum of particle A and B, that we have to find out. So let us start with the work done and then we can just work from there. So we can say that work done between point P and point Q. So here we are having two fields, electric field as well as the magnetic field. Okay. So we can say that our work done between the points P and Q let us suppose that work done is our WPQ, and that will be because of the work done because of the electric field plus work done because of the magnetic field. And we can find out the work done because of the electric field. Work done due to electric field, which is our WE, is equal to integration from the point P to Q, and we have force because of the electric field ds, and this is cos of theta. And force electric field is equal to charge multiplied by electric field. So we can write our electric work done because of electric field is equal to from point P to Q, and this is Q multiplied by our electric field ds cos of theta. QE we can take outside, so this comes as QE from P to Q ds cos of theta. And we can see that our electric field is parallel to x-axis, and the displacement is along the x-axis between the point P and Q is our 2a. Therefore, this integral part will be equal to 2a. So you can say that the displacement of the particle is 2a. Therefore, from P to Q ds cos of theta will be equal to 2a. So we get work done due to electric field will be equal to 2a q times E. So we found out that the work done due to electric field. Now we find out the work done due to magnetic field. Work done due to magnetic field, that is our WB, but we know that the work done due to the magnetic field is equal to 0 because the motion of the charged particle is in the xy plane and magnetic field is perpendicular to that plane. So work done because of magnetic field is equal to 0. So WB is equal to 0. Therefore, our total work done, that is WPQ, will be equal to 2AQ times E. So this is the work done, and we have to find out the rate of work done. And we are given that the kinetic energy, velocity at point P is given to us. So we can find out the kinetic energy at point P. So kinetic energy at point P will be equal to our half mv square. Similarly, we can find, let us call this as EP. Similarly, we can find out the kinetic energy at Q. Kinetic energy at point Q, which will be half m, velocity is given as 2v square, and we can write this as 2m v square. Let us call this as EQ. And based on this kinetic energy, we can also find out the work done, and that work done will be same, that is our WPQ. So we can say our WPQ will be equal to energy at Q minus energy at P. Energy at Q is our 2mv square minus half mv square, and this gives us 3/2 mv square. So this is also W. Let us call this equation 1 and equation 2. So we can simply equate equation 1 and 2. From equation 1 and 2, we get that 2AQE is equal to 3/2 mv square. And from here we can find out the value of electric field. Electric field is equal to 3/4, and we have this as mv square divided by A multiplied by Q. So this was our part 1, that is electric field. Option A is correct. Is correct. Now we have to find out the rate of work done. Rate of work done? Yeah, rate of work done, electric field at P. Okay. So the rate of work done is nothing but our power. So we say rate of work done, rate of work done is nothing but our power. And power formula, let us suppose that is our P, which we already know, that our P will be equal to force velocity cos of theta. And at P, the velocity is parallel to the electric field. Okay. So therefore we can say that let me write it, at P, velocity is parallel to electric field, that is our E. Therefore we can write that the power supplied by the electric field will be equal to QE times V. And V already we know is our, V already we know. It is in velocity. Okay, electric field we know. So we substitute it, we get this as Q, and this comes as 3/4 mv cube divided by Q multiplied by A. And Q cancel with Q, so this comes as 3/4 mv cube divided by A. So this is the power at point P, which is 3/4 mv cube. That is option B is correct. Is correct. And next we have to find out the field at Q, work done, rate of work done, that is basically power. And we already know the formula of the power is Fv cos of theta. Okay. And magnetic field, we know that is always parallel to the velocity in case of the magnetic field. So we can say that our magnetic force is perpendicular to the velocity. Therefore, theta is our 90. If theta is 90, we can write our power due to magnetic field is equal to 0. So our option C is also correct. C is correct. Now we come to the last part, that is our angular momentum. So we say angular momentum at Q angular momentum at Q, let us suppose that is given as LQ, which will be equal to our mass, and distance is our 2a, and our velocity is our 2v. Therefore we get our LQ will be equal to 4 MAV. Similarly, we can find out angular momentum at P. At P, let us suppose that is our LP, will be equal to mass, distance is our A, velocity is our V. Therefore, we get our LP is equal to MAV. We have to find out the difference. So we can say that the difference, our L is equal to LQ minus LP, that is 4MAV minus MAV, and it comes as, let us call this delta. Delta L, moment change in momentum or difference in momentum, is our 3MAV. So option D is incorrect because it is mentioned at 2 MeV. Option D is incorrect. Next question. We are given that three charge particles A, B and C, with charge is -4q, 2q and minus 2q are present on the circumference of a circle of radius d. The charged particle A and C and center O of the circle form an equilateral triangle as shown in the figure. The electric field O along the x direction is. Basic figure is given to us. We are given that three charges A, B and C are on the circumference, radius is given as d and their angle is given. It is also mentioned that AOC form an equilateral triangle. We have to find out the electric field only in x direction. So general formula for electric field we know that electric field at center electric field due to a point charge Q at a distance r. In this case our r is equal to d, so we can write our electric field will be equal to k q divided by d square. And we have to remember that if our charge is positive, suppose this is a plus q, then the electric field at a distance r, the direction will be away from the this. So this will be our electric field. And if the charge is negative, so suppose this is minus q at the same distance r, then the electric field will be towards the charge. We have to remember this thing. Okay. Therefore, for our charge at A, electric field will be toward the center. Similarly for C and for B, it will be away from the center. Okay. Let us suppose this is our EB, EA, and we have this as EC. And the angle along with the x-axis is given to us, and we are interested only in x component. So we can say that charge at A is our minus 4q and the angle is 30 degree with respect to x-axis. So we can say our EA will be equal to k 4q divided by d square, and we are interested in only x component. So we can say its x component EAX will be equal to our EA and cos of 30. So we can just write it that our EAX will be equal to, we have this as EA is our 4q upon d square, and we have cos of 30, that is square root of 3 divided by 2, and this 2 goes by 4, so we get this will be equal to our 2 root 3 kq upon d square. Similarly, we are going to find out for charge B. Charge B, its magnitude is plus 2q, and it is given at an angle of 150. So we can say our EB will be equal to K 2q divided by r square, d square in this case, and we need to find out its x component only. So we can say electric field at B, its x component will be equal to EB, and we have cos of 330. 1 second. Not a cos of 330, but cos of 30. Sorry, it's not 330, but it is 150. Yes, but in this case, we have to remember that the angle, this 150, this is the angle of charge, that is B. Okay, let me write here theta, and we need to find out the value of theta, which will be with respect to the electric field, not with respect to the charge. Okay, so we can say that direction of EB is away from B. So the vector from B points at 150 degree, and the field is opposite to that. Field is opposite to that. Therefore, opposite to that, so if we get our theta will be equal to, we can call this as 330, or we can call this as minus of 30, because with respect to the direction of the electric field. Therefore, we get our EBX will be equal to, our EB is 2kq upon d square, and this comes as cos of minus 30, which gives us 2kq upon d square multiplied by square root of 3 divided by 2. 2 goes with 2. So this gives us that electric field of B with respect to x will be equal to root 3 kq upon d square. Next is our charge at C. Charge at C, which is our minus 2q, and that is angle of minus 30, or if you require positive, we can consider it as a plus 330, okay, with respect to positive x-axis. And electric field at C will be equal to k 2q divided by d square, and its x component ECX will be equal to our EC cos of minus 30. So we get our EC in x direction will be equal to k 2q d square, and we have a cos of minus 30, that is root 3 divided by 2. 2 goes with 2. So this we get as root 3 kq upon d square. So therefore net electric field, that is our only x direction, total x component let us suppose it is our E of x. So we can write our E of x will be equal to x component of A plus x component of B plus x component of C, and we can take kq upon d square as common. Inside we are left with 2 root 3 plus root 3 and plus root 3. So this gives us 4 root 3 kq upon d square. So this is net electric field in x direction. So we have this as okay, there's substitute value of k, sorry. So we get this as 1 upon 4 pi epsilon naught 4 root 3 q upon d square. 4 cancel out with 4, therefore we get our E of x is equal to square root of 3q upon pi epsilon naught and d square. So option number 4 is correct. Is correct. Next question. We are given two infinite planes, each with uniform surface charge density plus sigma, are kept in such a way that the angle between them is 30 degrees. The electric field in the region shown between them is given by. So basic figure is given to us. We have two planes and each is having same surface charge density sigma plus sigma rather, and the angle between them is 30, and we are supposed to find out what will be the electric field of any point between them. So we already know the general formula that electric field is due to infinite plane electric field due to infinite plane, that is our E is equal to sigma upon 2 epsilon naught, and we have to remember that it is perpendicular to the surface and away from, because it is positive. So we can say perpendicular to the surface and away from the plane. So here we are having two surfaces and they are at a certain angle. So let me redraw the figure. So this angle is given as 30. So let us consider a point P, and we are going to find out the, you can say, electric field at this, net electric field at this point. This is plus sigma and this is also plus sigma, and let us assume that this is our sheet 1 and this is our sheet 2. So like I said, that is a perpendicular to the surface. So for sheet 2 it will be perpendicular in this way and direction will be away. Sorry. And it is perpendicular and its direction will be away. So let us suppose this is our E2 for sheet 2, and for sheet 1 let us draw a perpendicular. So for sheet 1, so this is our perpendicular here and this is perpendicular here. So in this case the electric field will be in this direction. Let us suppose that is our E1, and we have to find out the net electric field in the region. So we can say that our electric field due to sheet E1 electric field due to sheet 1, and it is at an angle, so we have to divide it into two components. Okay. For that we require the angle. Okay, so let us consider this point as A, this as B, and this point as C. So we can say in triangle ABC, angle A is our 90, angle B is our 30. So therefore angle C, in triangle AB and C, we can say angle A plus angle B plus angle C is our 180, and we know angle A is our 90, angle B is our 30 plus angle C is equal to 180. This gives us that angle C will be equal to 60. So we found out this angle is our 60, and let us call this point as Q. So now triangle PCQ, in triangle PCQ we are having angle C plus angle P plus angle Q is equal to 180. Q is 90, C is 60. Therefore we can write that our 60 plus angle P plus 90 is equal to 180, and this gives us angle P is equal to 30. So this angle is our 30. So based on this we can easily divide the electric field E1. Let me draw it separately. So this is point P, and we are having electric field E1 in this direction, and this angle we found out is our 30. Therefore we can say our component will be our E1 cos of 30, and the other component will be our E1 sine of 30. And we already know that our electric field due to sheet 2, that is our E2, is along y-axis. So based on this we can write that our electric field E2 due to sheet 2, electric field due to, we have sheet 2, that is our E2 will be equal to our E2 and in y direction. And similarly we can write, because of sheet 1, let us suppose we call this as our E1, this will be equal to our x component is also in a negative direction, so we can say this will be our E1 sine of 30, and we have this as minus of x unit vector and plus E1 cos of 30, and it is also in minus y direction, okay, coordinate we are taken like this, sorry. So this is our x and this is our y. So we can just find out our E1. So we can write that our E1 will be equal to sine 30 is our 1 by 2. So this comes as minus E1 by 2 x unit vector minus cos 30 is root 3 by 2. So this comes as root 3 E1 by 2, and this comes as our y unit vector. So we already know our E2 and we also know our E1. Very strange, it's not working. Okay. Next we are going to find out the net electric field. Net electric field, let us suppose that is our E is equal to E1 plus E2, and our E1 is our in y direction, so this comes as our E1 y unit vector plus E2 is our minus E1 by 2, and we have x unit vector minus root 3 by 2 E1 y unit vector. Sorry, I missed something. This is my E2. And because they are everything, so E1 will be equal to E2, and we know that our E1 is equal to E2 is equal to sigma upon 2 epsilon naught, which we can take common. Therefore we can write that sigma upon 2 epsilon naught, we are left with this is y unit vector minus, we have this as 1 by 2 x unit vector minus root 3 and y unit vector. We can combine our y unit vector, this comes as sigma upon 2 epsilon naught, and we get this as 1 minus root 3 by 2 y unit vector minus 1 by 2 x unit vector. So this is our net electric field, and option is 1 minus root 3 minus this, option 2 is correct. is correct. Next question. We are given an electric field vector E given as 4xi minus y square plus 1 j Newton per coulomb passes through the box shown in the figure. The flux of electric field through the surfaces AB, CD and BC, GF are marked as phi1 and phi2 respectively. The difference between phi1 minus phi2 is in Newton meter square per coulomb. Basic box is given to us and we need to find out the flux that passes through ABCD. So it means through this, and BCGF is through this, and here it is given as phi1 and here it is given as phi2. We have to find out their difference. So let me redraw this cube. And we are interested in two surfaces, that is A, B, C and D, and next is our BC and this is G and F. Here we are given phi1 and this is given as phi2, and axis, so this is our x-axis, this is our z and this is our x-axis, sorry, this is our y and this is our z. So first of all we are going to find out the direction of the aerial vector. So for the surface ABCD, our aerial vector will be along, so this will be the direction of aerial vector, and for our BCF, so let us call this as our A1 and this will be our second one, that is our A2. And in terms of magnitude, because we need to find out the flux, so for magnitude we need to the sides. Okay, so our AD will be our 2 units and our DC will be our 3 units. Therefore we can write that for ABCD, our area vector A1 will be equal to our A, and let us suppose there is n unit vector, n1 unit vector rather, and this is our A1. So A1 will be equal to 6 and our n unit vector is in z, again I have written wrong, this is our z and this is our y. So n unit vector is along z axis, so this comes as our k unit vector. So this is our area A1. Similarly for BC GF, we have our A2, that will be equal to A2, and let us suppose a unit vector N2, and for that we need its sides, and this will be our 3, 20, and here we are having 3, 2. Okay, so this will be our 2 units and this will be also 2 units. So we get area will be our 4 and our is in x direction, so this comes as I unit vector. Okay, so we found out the unit vector both. Okay. And next we are going to find out flux. Flux is the dot product of electric field as well as the area vector. So our phi 1, which is for the phase A, B, C, D, will be equal to our electric field E dot the area vector. Electric field E is given to us. We are given 4x I minus y square plus 1 j unit vector dot. This comes as 6 dot 6 times k unit vector. And so from here we get our I dot k j is 0. So we get our flux for the surface 1 will be equal to 0. So phi 1 is 0. Similarly, we can find out our phi 2. So our phi 2 is for the phase BCGF. So we have to remember, for this is our phi 1 and this is for phase phi 2. So phi 2 here had to be A1. So this comes as electric field dot our A2. Once again 4xi plus y square plus 1 j unit vector dot, and we this have our 4I unit vector and j. So this comes as phi for the second surface is 16 times x, and this phase is at a distance of, this distance is our 3. So value of x is 3. So you can say at x is equal to 3, we get plus at the second phase is equal to 16 multiplied by 3 is equal to 48. And we need to find out the difference, phi 1 minus phi 2. So you can say our phi 1 minus phi 2 will be 0 minus 48, giving us minus 48 and Newton meter square per coulomb. Per coulomb. So this is minus 48. Next question. We are given charges Q1 and Q2 are at points A and B of a right angle triangle OAB. See figure. The resultant electric field at point O is perpendicular to the hypotenuse. Then Q1 upon Q2 is proportional to. So we are given that the resultant electric field is perpendicular to the hypotenuse and both charges are positive. So the direction of the electric field will be away from the both. So for B, suppose this is our EB and we are going to have our EA, and the resultant electric field obviously will be in this direction, but it is mentioned here that it is perpendicular to the hypotenuse, so this will be 90 degree. So let us suppose this is our resultant electric field E, and if we have that this angle is our theta, so we can say that this angle will be our 90 minus theta. So we get this angle will be also theta, and we get this angle is also equal to theta. So we can say that if we, okay, they are written in the Q1 by Q2. Okay, not an issue. So if we complete this parallelogram, from here we can say our tangent of theta will be equal to our perpendicular oblique base, that is our EB upon EA, and we can find out our EB and EA. We can say electric field at O due to charge at first charge, let us suppose, is charge at A, distance is x1. Therefore we can write that our EA will be equal to Q1 is at A, so this comes as K Q1 upon x1 square. Similarly, we can say at charge at B and its distance is x2. Therefore we can write our EB will be equal to K Q2 upon x2 square. And yeah, the charges are different. So we can simply substitute the value of the electric field. Okay. So let us put this here our equation 1. Therefore we can write that from equation 1 we have our tangent of theta is our EA upon EA. So we get this as K Q2 upon x2 square, K Q1 upon x1 square. And here K and K cancel out. This comes as Q2 upon Q1 multiplied by x1 square upon x2 square. And the tangent of theta is also equal to our x1 upon x2. So from here we can say this square cancel with x1 and this square goes by x2. We need to find out Q1 by Q2. So we get Q1 by Q2 will be equal to x1 by x2. And this gives us that option C is correct. Option C is correct. So this completes the part 2 of the year 2020, and all these part 2 questions were from the mains only. Part 1 also consists of only the mains. The next part we will try to cover the remaining questions from 2020 and if possible mains as well as advanced, or we can do separately also. So this completes the part 2. Thank you.